AI and AMP, Data Centers in Space. A comprehensive guide 2026 satellite dish executive overview. Space is no longer just for exploration, it's becoming a computing platform. Space is transforming into a platform for computing and artificial intelligence, where companies like Amazon, Blue Origin, SpaceX, NVIDIA, and Google are developing orbital data centers that could deliver 10x to 40x more energy per square meter compared to Earth-based systems. This represents a fundamental shift in how humanity will power artificial intelligence for the coming decades. Battery: the energy crisis. Why space? The problem on Earth: AI is driving explosive growth in data center construction on Earth. US spending on data center infrastructure jumped nearly 70% between May 2023 and May 2024. Energy consumption at those facilities could double or triple by 2028, accounting for up to 12% of US electricity use. Key statistics: a single large-scale AI training run can consume as much electricity as a small city for weeks. The International Energy Agency projects that AI data centers will consume roughly 1,000 terawatt-hours per year by 2026, representing 3 to 4% of total US electricity consumption and rising sharply. Communities from Virginia, Georgia, and Texas to Frankfurt, London, and Amsterdam are pushing back against land use, water consumption, and power draw from hyperscale data center campuses. The space solution, unlike Earth-based centers, orbital facilities offer unlimited solar power. Sunlight hits satellites 36% stronger than it reaches Earth's surface because there's no atmosphere blocking it. Solar panels stay bathed in light almost constantly with zero weather interruptions. Natural cooling. The cold background of space, near -455 degrees Fahrenheit, creates an opportunity. Waste heat from the data center could escape into space through radiators, keeping the electronics cool. The vacuum of space lets heat radiate away naturally into the freezing void with no water needed and no environmental trade-offs. No environmental opposition, zero land use, zero local permitting fights, and zero water consumption concerns. Light bulb technical advantages. 1. Energy efficiency. Space-based systems remain solar-powered for more than 99% of their operations, depending on the orbital plane, minimizing battery requirements. No grid dependency or fuel deliveries require direct sunlight conversion without atmospheric losses. 2. Cooling without water in space. There's no convection, only radiation. Heat radiation into the vacuum provides passive cooling without mechanical systems. Traditional Earth data centers require millions of gallons of water daily for cooling. 3. Processing power per ton. SpaceX's approach, launching 1 million tons per year of satellites generating 100 kilowatts of compute power per ton, would add 100 gigawatts of AI compute capacity annually, with no ongoing operational or maintenance needs. 4. Scalability through manufacturing. Scaling terrestrial data centers requires years of construction. Scaling the orbital fleet requires manufacturing more satellites, a factory problem. Rocket: major players in AMP projects, 2026, SpaceX. The industry leader. The AI-1 satellite, June 2026. On June 8, 2026, SpaceX unveiled the AI-1 satellite, the first generation of its orbital artificial intelligence compute platform. The AI-1 is a 70-meter wingspan solar-powered orbital compute node with 150 kilowatts of peak AI compute designed to run artificial intelligence workloads from space. The massive vision. SpaceX filed a request with the Federal Communications Commission to launch up to 1 million solar-powered satellite data centers into low Earth orbit, a constellation the company describes as the most efficient way to meet the accelerating demand for AI computing power. Key partnership. SpaceX has a reported $1.25 billion per month contract with Anthropic to provide AI compute, a figure that makes the orbital data center ambition look less like a moonshot and more like a logical infrastructure scale-up of an existing revenue line. Vertical integration. In February 2026, SpaceX acquired xAI, merging his AI company into the rocket company. The combined entity now spans rockets, satellite internet, Starlink, direct-to-mobile communications, the X social platform, and AI compute infrastructure. Manufacturing capability. To build 1 million satellites, SpaceX is building the Gigasat factory in Bastrop, Texas, a site spanning more than 1,000 acres with over 11 million square feet of planned building capacity. NVIDIA, the chip architect. NVIDIA announced that its latest accelerated computing platforms are unlocking a new era of space innovation, bringing AI compute to orbital data centers. The NVIDIA Space One Vera Rubin module, IGX Thor and Jetson Orin platforms deliver data center class performance and edge AI inferencing for orbital data centers. Real deployment. Companies like Aetherflux, Axiom Space, Kepler Communications, Planet Labs, Sophia Space and StarCloud are using NVIDIA accelerated computing platforms to power next-generation space missions. Technical specifications. The Vera Rubin Space One module includes the IGX Thor and Jetson Orin, which deliver energy-efficient, high-performance AI inference, image sensing and accelerated data processing to enable true edge computing on orbit in a compact module. Axiom Space. First operational system Axiom Space launched the first 2 orbital data center nodes successfully to low Earth orbit on January 11, 2026. These ODC nodes will lay the foundation for space-based cloud computing, addressing growing global needs for secure, scalable, and cloud-enabled data storage and processing. How it works. A satellite collects raw data, images or telemetry. Instead of sending all raw data immediately to Earth, it sends to a nearby orbital data center node via optical link. The Axiom Space compute hardware runs processing, inferencing, filtering images, detecting features, compressing files, or running AI, ML models. This results in smaller or more valuable data being sent either downward, to ground, or to another in-space node or stored onboard. StarCloud. Large-scale Vision StarCloud has plans for an 88,000 satellite constellation aimed at delivering on-orbit compute at scale. In September 2024, Y Combinator-backed StarCloud released a white paper detailing plans to build multiple gigawatts of AI compute in orbit. In 2025, StarCloud deployed an NVIDIA H100 class system and became the first company to train an LLM in space and run a version of Google Gemini in space. Google. Project Suncatcher. In November 2025, Google announced its Project Suncatcher initiative, exploring the concept of compute in space. Google is exploring Tensor Processing Unit (TPU) clusters in space and hardening processors and testing lightning-fast laser links for its own space projects. Gear Hardware and AMP technology stack computing platforms NVIDIA Vera Rubin module, space-optimized GPU NVIDIA IGX Thor, Edge AI inference processor NVIDIA Jetson Orin, compact AI accelerator custom chips. Companies developing radiation-hardened processors, power systems, high-efficiency solar panels, 50% conversion efficiency, lithium-ion batteries for eclipse periods, direct coupling to solar arrays for continuous power cooling systems, radiative cooling panels, passive heat dissipation, no active cooling needed, vacuum as the ultimate coolant, communication, optical intersatellite links, laser communication between satellites, ground station connectivity, low latency data transmission, radiation protection. A major engineering hurdle is handling radiation. Chips operating in space must be radiation hardened to survive cosmic rays and solar radiation. Bar graph current status, 2026, what's already happening? Axiom Space's first 2 orbital data center nodes successfully launched to low Earth orbit on January 11, 2026. In January 2026, a team from the University of Pennsylvania presented a tether-based architecture for orbital data centers at the AIAA SciTech conference. In May 2026, Edge Aerospace was awarded a contract by the European Space Agency under its Space Cloud program to study use cases, architectures and implementation roadmap for orbital data centers. SpaceX unveiled its first piece of hardware for orbital AI data centers, the AI-1 satellite, on June 8, 2026. These aren't distant dreams. Axiom Space launched working orbital data center nodes in January 2026, and Google is hardening processors and testing lightning-fast laser links for its own space projects. Robot How AI analyzes space data beyond building data centers in space. AI is revolutionizing how we analyze data from space. 1. Mars exploration. When the ESA-led Rosalind Franklin rover heads to Mars, a NASA machine learning algorithm will analyze samples collected by the rover's coring drill. The algorithm will identify organic compounds, greatly speeding up the process and saving scientists time as they decide the most efficient uses of the rover's time on the red planet. NASA's Perseverance rover on Mars relies heavily on AI to navigate the Martian surface independently and in real time, unlike earlier rovers that relied more on manual human input. Applications. ML can identify geological features, monitor environmental changes, and detect anomalies on planetary surfaces. Neural network models are testing the interpretation of Mars satellite imagery. Such a neural net could enable a satellite to detect a new impact ejecta, evidence of a meteorite impact, and alert other spacecraft or take follow-up images. 2. Lunar analysis. Convolutional neural networks, CNNs, automate crater identification on the Moon by analyzing high-resolution images from NASA's Lunar Reconnaissance Orbiter. Lunar craters are critical markers for geological analysis, hazard mapping, and landing site selection. 3. Earth observation. NASA uses multiple machine learning approaches for Earth observation data, including GeoWeaver, an open-source platform for enabling ad hoc management of NASA Earth data-driven hybrid AI workflows, and PangeoML, open-source tools and pipelines for scalable machine learning using NASA Earth observation data. Crew members aboard the International Space Station collect imagery during studies like crew Earth observations. Historically, image processing has been a manual task, but now researchers are assigning it to artificial intelligence. 4. Large-scale data processing. NASA's telescopes collect massive amounts of data about deep space every day, and AI can help process this data faster. Machine learning models can analyze light curves to predict cosmic events like supernovae and gamma-ray bursts. AI has also been used to identify gravitational waves caused by massive cosmic events, quickly analyzing data from observatories like LIGO and Virgo. 5. Autonomous decision-making. Machine learning enables autonomous rovers to navigate complex terrains, avoid obstacles, and make real-time decisions. NASA's Mars rovers use ML to enhance navigation systems, allowing for more efficient and safer exploration. Warning: major challenges in AMP, technical hurdles. 1. Cooling in a vacuum. The biggest challenge, getting rid of heat, is surprisingly difficult in space. There's no convection to carry heat away, only radiation into the vacuum. 2. Radiation damage. Electronic components degrade faster in space, requires expensive radiation-hardened processors. Bit flips and data corruption are risks. 3. Maintenance and AMP. Repairs are extraordinarily expensive, and every pound launched into orbit carries a significant cost. Energy generation and storage, thermal management, radiation exposure, transportation, and in-orbit maintenance all pose significant challenges. 4. Launch costs. Google's feasibility study suggests that if launch costs to low Earth orbit reached $200 per kilogram, the launch cost for data center satellites could be cost-effective. They project this may occur around 2035 if SpaceX's Starship project scales to 180 launches per year. 5. Orbital debris and AMP. Space traffic limited orbital slots. Available space debris is an increasing hazard. International coordination requirements. 6. Latency sensitivity. More feasible early applications may be those that are less latency sensitive and more tightly connected to space operations. Examples include processing Earth observation data from satellites, military, intelligence data processing, scientific computing related to space missions, or specialized computing for satellites and other space assets. 7. Technology obsolescence. Technology obsolescence of AI data centers is a concern, and difficult maintenance in space imply the single-use purpose of those space data centers. To extend lifetime, space infrastructure will require either refueling or orbit raised by a servicer, which will increase operational costs. Money bag economic implications market projections ABI. Research forecasts nearly 18,600 active data centers by 2035, driven by falling orbital compute costs and technological innovations. Currently, Amazon, Blue Origin, SpaceX, NVIDIA, and Google show interest in developing this technology. Investment activity. The race to put computing infrastructure in orbit is accelerating as hyperscalers across cloud, AI, and space compete. U.S. spending on data center infrastructure jumped nearly 70% between May 2023 and May 2024, and companies are now looking to orbit as the solution. Cost-benefit analysis advantages. Eliminates water cooling costs, no land acquisition or zoning battles, near unlimited solar power, no grid dependency disadvantages. High initial launch costs, expensive repair, maintenance technology, obsolescence cycles, current launch costs. $1,500 per kilogram with Starship. Still challenging crystal ball future prospects. 2026-2035. Near term. 2026-2028. Multiple companies will launch prototype orbital data center nodes, focus on edge computing and space-based services, real-time testing of cooling and power systems, AI, ML training runs in space becoming more common medium term. 2029-2032. SpaceX's path to becoming a major player in orbital computing hinges on several things happening. Dramatically reduced launch costs from Starship, manufacturing capacity at the Gigasat facility, and reliability of orbital systems operating for years. Hybrid ground and orbit computing becoming standard, specialized space-exclusive AI workloads, emerging environmental benefits becoming measurable long-term. 2033-2035. ABI Research forecasts nearly 18,600 active data centers by 2035, with falling orbital compute costs and technological innovations driving growth. Possible transition of baseline AI compute to space Earth-based centers handling latency-sensitive workloads, new industrial applications in space economy, upward trend, practical applications emerging in 2026. 1. Earth observation and AMP. Climate monitoring, satellite imagery analysis happening in orbit, real-time environmental monitoring, disaster response and tracking. 2. Military and AMP. Intelligence, classified data processing in secure space-based systems, real-time threat detection. Defense and space security, along with space-based quantum communication, are enhancing global security and data encryption. 3. Scientific research processing, massive telescope data, JWST, future observatories, deep space mission planning, real-time analysis of cosmic phenomena. 4. Space industry supporting satellite constellation management in space, manufacturing, planning, autonomous spacecraft operations. 5. iModel training. StarCloud became the first company to train an LLM in space and run a version of Google Gemini in space. Globe environmental impact, positive aspects, eliminates billions of gallons of water consumption, no land footprint or habitat disruption, reduces local power grid strain, eliminates electromagnetic pollution from terrestrial stations, concerns launch emissions, add to atmosphere, space debris accumulation, e-waste in orbit. Difficult to recycle. Orbits are, like any resources, a limited physical and electromagnetic resource available for all mankind. Environmental impact of launches needs to be addressed.